It's a great pleasure to be here today. Thanks so much to the Women in Quantum organizers for the opportunity to speak with you. I'm just going to share my screen. Of course, I also want to thank the sponsors, Keysight, and all of the other great companies like IonQ who have also supported the event today. It's a nice moment that we're actually here celebrating the women who are in quantum technologies. So I'm very pleased to share with you today the vision as we see it for the future of quantum communications. We, in this case, being Qunnect, the company that I'm CEO of. And our particular interest is in the area of distributed entanglement networks. So I'm going to talk to you a little bit about the progress of where the field is and where we see it going. So quantum networks, as we've seen over the past, probably a handful of years, but particularly in 2021, have seen just a tremendous amount of growth and are rapidly evolving. So in the very beginning of the year, China demonstrated a 4,600 kilometer ground satellite QKD network through trusted nodes across their country. It's a real tour de force in the field. And as recently as June, there were a number of really amazing articles that came out, some which garnered the cover of Nature, and where quantum communications was highlighted. And in Nature Photonics, Toshiba announced a breakthrough in their twin field protocols, which allowed them to get links that were as long as 600 kilometers in terms of transmission distance. And I'm going to speak about each one of these a little later on. But I think it really is a hot time to be in quantum networking, and it's exciting to see where it's going. So the timeline, which again, this is by no means inclusive, it's just some interesting little moments along the way to give everyone sort of the same starting point. IDQ, ID Quantique, in Switzerland is really one of the first hardware providers in quantum communications, and they've been building encoders and decoders since the mid-00s. And were founded maybe half a dozen years before that. But that at the same time, so for the others of you who are on Maria Spiropoulos' talk earlier today, she had a throwback to the very early announcements of the first 10-node network that DARPA funded in the U.S. in the Boston area. So that was sort of coincident, again, all in the mid-2000s. And since that time, a lot of research and development has been happening in the academic side to try to bring these things into really network scale. And notably, China entered the game with a very serious commitment, launching the first quantum communication satellite, Messius, which later, just a year later, was used in order to transmit some secure keys in order to host a video conference between China and Austria. So Sergei Wang-Pan's group and Zeilinger in Austria. And then as QKD has evolved, so have the protocols. So Toshiba introduced this idea of this twin field QKD protocol, which has now become one of the powerhouse protocols in the field, which recently had that announcement for the 600 kilometers. And as we see, as 2020 started, we've had a number of very interesting things happen. So again, from Maria Spiropoulos' group and also the Fermilab and JPL collaborators, there was a demonstration of quantum teleportation over 44 kilometers just at the transition of the year. That large QKD network was demonstrated in China also at the beginning of the year. And then these recent papers, the ones that I mentioned, they were on the cover of Nature, as well as the demonstration that we just saw literally last week from the Delft group being able to do MDI QKD between two cities, Delft and The Hague. So although this is really inspiring time to be working in the field, there's still a tremendous number of challenges to implementing quantum networks in the real world, which I think you've heard from also several of the speakers today. First and foremost is really the invention of new devices. We need things that go beyond the first generation technologies to support the networking protocols that are going to be needed in order to actually go towards what everyone keeps calling the quantum internet. And those protocols which are going to be run on those devices also need to evolve. Single photons, particularly entangled photons, are incredibly fragile. So real-world losses, both from interfacing multiple devices and sending photons through channels like fibers, all need to be dealt with in terms of how these protocols will run in order to really function as networks. There's also two real engineering challenges on the back end of this. Infrastructure compatibility is a big one. All of the fiber that was laid across the world was not done so with the intent that it would host single photon communications. So we need to be able to build devices that are compatible with this so we can utilize the infrastructure which is already there. Of course, a lot of quantum devices are not natively at telecom either. And if we can build the devices, then we also have to worry about whether they're affordable and practical to scale. So building robust devices that can be deployed remotely at reasonable costs and with low maintenance are all challenges that exist out there. So as I said, QKD had quite a triumph in January 2021 with this very large network extending across China and a number of different interesting network topologies. While the trusted node system is something which has shown great functionality, the concern, of course, is that ultimately this is not a very practical protocol, and it doesn't actually distribute entanglement from one to the next. It basically is a series of links where you repeatedly decode and re-encode over each node. So the implementation is rather expensive and laborious, but they did receive very interesting transmission rates. Again, this looks a little bit like the dial-up modem days, but it's still very impressive that on average they had about 50 kilobits per second, as is what we know we can do in digital, but you have to start somewhere. And QKD has been evolving. So as early as 2012, this idea of doing a measurement device independent QKD protocol was put out there, and this is actually in the background of what I'm going to continue talking about today, which are these repeater protocols. The idea is the fact that you have now a center node that serves as the measurement station so that you aren't transmitting directly from Alice to Bob without going through the center node. And as a result, neither Alice nor Bob has to sift the keys as they do in the standard QKD protocols so that it's measurement device independent. And then later on, as I mentioned, Toshiba brought a new protocol to the game called twin field QKD, which has been extremely interesting in the QKD field because now, as they've had more and more implementations of it, they start to approach this solid line, which you see across the graph here, which is basically the theoretical limit of what you can do in a fiber channel in terms of transmission losses. And their newer paper, which I'll speak about in just a second, actually exceeds what they reported here. But you can see that there's a gap before you actually get up to something where the secret key rates are significantly better, which are the theoretical bound if you actually implement a new type of protocol, which we would call repeating. And one of the challenges in twin fields has been that the phase locking distant sources was never simple. In order to sift the keys, they look for a phase matching condition. So that is actually what this new paper addresses directly. So they have a new type of protocol, this TWCC SNS protocol that they're running. And the TWCC stands for two-way classical communication. And basically what it does is you take two different wavelengths from originating from two different lasers, which themselves don't actually need to be phase locked, and you provide an active feedback signal for effectively establishing a phase lock between these outer nodes and the center node Charlie. And again, this looks very much like what we were talking about with the MDI QKD types of protocols before, where you have a center node that has a measurement station in the center and two outer nodes which can send photons to the center. What they established in this, which was really interesting, is that they had the ability to actually go beyond this solid line, which again is the theoretical limit for transmission without a repeater. And that's how they received the sort of like landmark now that they're up to 600 kilometers per link. It's something that we would call sort of phase-locked quasi-quantum repeater-like, which is the language that they use in the paper, transmission between nodes. But of course, we all know that we'd like to move also beyond QKD to more sophisticated types of protocols. The realities are that fiber losses are always going to be hard for single photon communication, even with ultra low loss fibers. So the real solution is to do some type of new entanglement distribution between Alice and Bob, which colloquially we've all been calling quantum repeating. And the most common protocol behind that is called entanglement swapping. So entanglement swapping is a fairly simple concept. The idea is that you have two sources which produce entangled pairs separately. And one photon from each pair is sent to a central station where a Bell state measurement is performed. And when that happens, the remaining two photons, in this case labeled 1 and 4, are now mapped onto the same entanglement state. This was proposed in the early 90s, and then the first experimental demonstration was from Zeilinger's group in the late 90s. And now we're actually starting to see experimental implementations, in fact, in some of those very recent Nature articles. So to use those for quantum communication, what you would do is you would take each one of these elementary links, which, again, each orange dot is an entanglement source. It produces a pair. There's a Bell state measurement station in between. But the problem is that you need to hold on to the entangled photons that remain in the outer two nodes. And the way that you do that is with quantum memories. So therefore, quantum memories have really become an enabling technology when we start talking about the concept of repeating. And the way that it's shown here, the idea is that you have all of these elementary links, each of which performs a Bell state measurement and holds their photons in the memories. And then you cascade that up a hierarchical chain by now exchanging entanglement between a Bell state measurement between elementary link 1 and 2. And eventually you end up being able to communicate between the two most distant nodes. So as an enabling technology, of course, they're there to assist in things like entanglement swapping, which you see here in the diagram on the right. This is a version done with cold atom memories from Zhiwang Pan's group. But they also can actually increase the probability of doing successful MDI QKD. So quantum memories are really, in this sense, a very enabling technology for whatever the next steps of quantum communications are. And for MDI QKD, again, entanglement sources are non-deterministic in nature, or tend to be, although there are some examples on the deterministic side. In order to make sure that you always have a successful Bell state measurement, you need to control the timing of arrival at the Bell state station. And the easiest way to do that is to have a memory within the line, which allows you to store and release in a way which actually turns a non-deterministic event into a deterministic one. So because of that, there are a lot of people trying to develop interesting quantum memory technologies. As I mentioned before, there are these atom clouds, cold atom cloud technologies, which are worked on by a number of groups. Similarly, there's also trapped single atoms, which can do the same thing. And then there's a host of solid state technologies, those which are nitrogen vacancy centers in diamonds and silicon vacancy centers, done by a number of groups which you'll recognize here. And also, very recently in those Nature articles that I mentioned are these concepts of rare earth doped crystals, which have been demonstrated as powerful new technologies as well. What Qunnect works on is a little different than all of the other types of memories which you see here. What you'll notice, which is in common about all these, is that they are all in the tens of milliseconds or longer in terms of storage times. But they're able to do that because they all are operating under either extreme cooling and or vacuum and or both. So the idea of having to have deal fridges everywhere, which I think we were listening earlier to the Verizon speaker mentioning that it's not something that we think is going to be so easily scalable. So there is a need for new inventions of technologies which can operate without the sort of cumbersome infrastructure. And that's exactly what Qunnect does. We build room temperature operation quantum memories. Our storage times are not nearly as good as what you can get in these cold atom cases, but they're still quite good. In fact, 100 microseconds is more like 300, 350 microseconds in practice. But hopefully these things will end up getting up to about 1 millisecond by the time the technology matures. So tell you just a little bit about what we do. So we build these dual rail memories which operate on this phenomenon called electromagnetically induced transparency. And the idea is that you have atomic vapor, in our case, rubidium vapor, which is inside of a vapor cell. You basically use a control laser beam and a signal laser beam in order to communicate into the vapor cells. So the control laser beam effectively makes the medium transparent or absorptive, depending on whether it's on or off, which allows you to slow down the light which is coming into the medium. And then by just simply turning the control laser on and off, you're able to release the photon on the other side. The reason that we have a dual rail structure is because we separate the horizontal and vertical polarization components, because the qubits that we work with routinely are polarization qubits. Of course, there are a lot of advantages to this, in the sense that the optics are relatively simple, but you do need to be able to separate the control laser from the signal laser on the backside. And although we've drawn them as relatively simple here, you have to have some very serious filtering in order to make this work, and that's exactly what makes qnect's technology special. We've learned how to do that well. We've also learned how to control all of the noise sources within the vapor cell itself quite well. So here's a picture of our newest release. It's a rendering of our room temperature quantum memory beta unit. We have sales to our research collaborators literally this month. And the unit slides into just a standard rack. And you can see an actual photo of the device here. This is our premiere. This has never been shown before. And its performance specs are basically that the fidelity of the unit is now in the sort of mid-90s, which is directly related to the signal to noise of the device itself. And signal in this case is how many successful photons in versus the other noise photons you have that are going through the system. Can you distinguish the signal from the noise? And again, we've spent a lot of time in the last 6 to 9 months. Our scientists have worked hard on bringing this number up. And we have plans to do even better as we keep going forward. Similarly, the coherence time is now in a few hundred microseconds. This 100 is more on the conservative side, and we hope to bring that up also by the time we push this to another instrument. In order to make all of this work well, we also need to have a fair amount of support software that not only does remote control and monitoring, but also auto-aligns some of the devices within the unit. So that's something that we've been working on actively in the lab as well, and will be incorporated into our later units. So it's very exciting to see this come to fruition. But beyond the memory, we also need a number of things to make a quantum repeater actually work. So those elementary nodes, here's another one of those 3-node systems where you have a left and right node with a center in between to do entanglement swapping. They actually need other things. So first and foremost, you also need entanglement sources, which are compatible with the memories. And then you need a number of support devices. So in this case, you need a timing standard. So that's the sync that I've drawn here. You need frequency standards, which is the lock that I've drawn here at any one of these outer nodes. And then you need the Bell state measurement device in the center, which is what I've called here the swap, and any calibration devices, because as you look at all of these papers in the literature now, if you send things down long fibers, any photon which is traveling down a long fiber has a tendency to drift, and you want to be able to correct for that. So Qunnect is actually building all of these instruments. We have 4 of the 6 instruments actually in prototype stage, and 2 of them have actually been tested on real fiber beds on Long Island. So I just want to switch for a moment and give you a little overview on the literature of some of the exciting stuff that I mentioned on that first slide. So this is almost an identical setup, 2 outer nodes with a central node that appeared in Nature in June of 2021. And basically what they've shown here is the ability to again, create entangled pairs at either one of the outer nodes. One photon from each one of the pairs is stored in the memory at each one of those nodes. The others travel into the center node where there's actually a Bell state measurement. And then they release the photons which are at the memories and analyze those to see how effective they've actually been able to actually store and release, as well as herald the information from the photons themselves. So they estimate, these memories were highly efficient. They're about 95% fidelity at very short storage times. And of course, as you push the storage times up, the fidelity goes down. But the verification of the photons for the fidelity of the overall process, they still estimated as being in the high 90s, in the low 90s, which is still incredibly impressive. And in the exact same issue of Nature, there was another paper. Both the previous slide and this slide are using rare earth memories. So in this one, they were actually using an entanglement source which was able to produce telecom frequency photons. So, bichromatic, as you're seeing here, actually, the different color lights. So they're able to send one frequency, again, to a central node. So these are 2 outer nodes and a central node. the pair is created, one goes to the center node, the other one goes to the memory, and then those are analyzed. What was interesting about this paper is that the quantum memories are a special type of memories that actually can store photons in multiple modes. So they were able to demonstrate this 25 microsecond storage with many storage modes actually demonstrated. And the verification of the photons released from the memory revealed a fidelity of the overall process of being able to store and release versus those which were sent to the center of, again, something in the low 90s. So it's a very exciting time. Between this paper and the previous paper, you're seeing rare earth memories doing very interesting things in realistic repeater type setups as elementary links with operations which garner a lot of confidence that we can start to push these towards being real networking technologies. Similarly, there's a number of other papers which have come out trying to expand this into multiple nodes. So here's two notable ones, one from the Delft group and one from Jerome Peng's group in China. So this is the one on the right from the Hansen group. Basically, these are demonstrations of just showing you can now put more memories into the system and learn to manipulate between multiple nodes and try to do basic logic functions. So this is sort of a bold slide. I don't know what the future is going to hold, but if I had to give a sort of prediction, I think that right now what you're seeing this year is that there are a lot of demonstrations of elementary links for quantum repeaters that are being demonstrated in laboratories while the memory and source technologies are starting to advance. And on the QKD side, you're seeing the twin field technologies mature and more fiber beds all across the world start to come online. So I think in the next 2 years, what we're going to see is that some of these multi-node combination fiber and satellite demos are going to start happening, trying to demonstrate basic repeater protocols, and that the memory and source technologies, including those from Qunnect, are going to start to become commercially available. And as we heard earlier in the talk from Keysight and Verizon, standards are very important. Right now, there are no communication standards defined for quantum, so we really need to be paying a lot of attention to that over the next 2 years, because it's going to only go into expanded use in these other types of industries whenever that actually happens. And that's absolutely true when telecom enters the game. So then I'm hoping that in 2025, we're starting to see some of those repeater techs pushing forward, and we start to see the first interfacing of quantum computers to quantum networks, which will be extremely exciting. And of course, the quantum secure infrastructure, which we hope will be more mature by that point, will also start to become available as services. And then maybe we'll eventually get to the big idea of the quantum internet. So just as a last slide, I wanted to remind you that really big computers like the Cray in the old days, right, were really good at solving hard problems in isolation. But the internet enabled a huge number of things, including distributed computing. And this is a screenshot from the old days one of the first distributed computing algorithms many of us had on screensavers was the old SETI desktop processing tool, which processed the data from radio telescopes to search for extraterrestrial life. But we know that huge numbers of industries were enabled because of actually being able to bring the digital network online. And of course, the promise is as rich for the quantum network. So I want to thank everyone. Qnect is located in the Brooklyn Navy Yard, so we are just across from Manhattan. If you are around, please drop us a line and visit our facility. We are funded by a number of federal agencies and venture funds, including Quantum Nation, which, as everyone was talking about earlier, with the Quantum Benchmark company. That was another one of the Quantum Nation-supported companies that recently was acquired by Keysight. And if you'd like to connect, please do. My information is below.